Dear students, in this class we will discuss about the diffraction of electrons at a single slit. That is, diffraction of electrons at a single slit. Let me tell you, this is an experiment to illustrate the Heisenberg's uncertainty principle. That is, in the previous class we have discussed about the gamma ray microscope experiment. That is also an experiment to illustrate the Heisenberg's uncertainty principle. In the same way, we have one more experiment. What is known as the diffraction of electrons at a single slit. So this is also an experiment to illustrate the Heisenberg's uncertainty principle. So we know, as per Heisenberg's uncertainty principle, that is delta x into delta px is greater than or equals to h divided by 4 pi. So what is delta x? Delta x is the uncertainty involved in the measurement of position. What is delta px? Uncertainty involved in the measurement of momentum. So, as per Heisenberg's, we know that whenever we try to make the measurement of position and momentum of a subatomic particle like electron or proton or neutron, it is very impossible. If at all we make an attempt to measure the position and momentum of these particles, which are very small in dimension, it always involves a certain amount of error. So that error is given by what? Delta x into delta px. Delta x is the error involved in the measurement of position. Delta px is the error involved in the measurement of momentum. So this error, the product of these two is always going to be greater than or equals to a quantity known as h divided by 4 pi. So this Heisenberg's uncertainty principle we are going to prove here by one more experiment, what is known as diffraction of electrons at a single slit experiment. Let me remind you, so this is not a real-time experiment. This is not a real-time experiment. This is again one more thought experiment. So this is a thought experiment. Using that we can verify the Heisenberg's principle. So for that, to verify Heisenberg's principle, what is required is we have to calculate delta x and we have to calculate delta px. And we have to show that the product of these two is either equal to h divided by 4 pi or greater than or equals to h divided by 4 pi. So for that, so this is the experimental setup. So if you look at this experimental setup, so what we have here is, so this is a small window, delta x corresponds to a small slit or a small window having the width of delta x. So through this small window or a small slit, the beam will enter into this small window or a small width and it undergoes diffraction. So this is the screen, this is the slit of it delta x, right? And incident light will enter into the small window and it undergoes diffraction. You know that the diffraction takes place always whenever the light and the size of the object, in this case the width of the slit, if both are comparable, then it undergoes diffraction. So for diffraction takes place, the size of the dimension of the light and the dimension of the object both should be comparable. So here the size of the window and the size of the light, if they are comparable, then it undergoes diffraction. What is diffraction? The bending of ray of light. So the incident light which was traveling in the straight direction, instead of traveling straight, what happens? It undergoes bending. So as a result of that, what we get on the screen? On the screen we get a diffraction pattern. What is diffraction pattern? That is, at the middle we get a maxima. That is, we will have a bright band having the maximum intensity. That is corresponding to this. We have a central maxima, and on either side we have dark bright fringes. On this side also we have dark bright fringes will be obtained. So we get a diffraction pattern on the screen due to the diffraction taking place by the light which is entering into a small window. Now, what we are doing in this experiment is, instead of passing a light beam, we are passing an electron beam. We are passing a beam of electrons. The position of those electrons which you want to find out. So when you pass a beam of electron, let's take for example a single electron which is entering into this small window. Here the delta x looks so large, but actually imagine the size of the electron. So the slit width is almost comparable to that of the size of the electron. So means the slit width is very small. So as a result, when the electron enters here, that electron undergoes diffraction and the diffraction pattern will be obtained on the screen. No. What is our job? We want to find out delta x. So what is delta x? The error involved in the measurement of the position, right? No. So in this case, when you pass the electrons, if you want to find out delta x and delta x, that is, we have to find out the position of the electron and we have to find out the momentum of the electron, right? So electron enters here, so it encounters a slit here, means at this point we are trying to find out the position of the electron. So what will be the position of the electron, or what is the error involved in the measurement of position of the electron? That will be taken as equals to what is known as delta x. Why delta x? Because the window width is so small that the uncertainty or the error involved in finding the position of the electron will almost be equals to the width of this, that is going to be delta x. It is going to be delta x. So this gives you what is known as delta x, right? Means we are trying to find out the position, or in other words the value of delta x with help of the slit width. Then from this point onwards, what happens? The electron gets diffracted, means it is traveling with a momentum. It is traveling with a momentum. So this is one beam and this is another beam, right? We are taking a certain point on the screen. Let's say for example this is the point on which we are trying to find out the momentum value, right? So for that, what we have done? So we have taken the mean. This indicates what? This is the mean deviation. Means if this is the slit width, rays will be traveling here like this, like this, like this, like this. There will be n number of rays. What we are doing? We are taking the mean of all the rays. So this is the mean of all the rays. This mean ray is making an angle of what? Is making an angle of alpha with respect to the original incident ray. This is the undeviated ray, right? This is the mean deviated ray. So this mean deviated ray is making an angle of what? Making an angle of alpha with respect to the original beam, which is having a central maxima here. So this is the central maxima, the first minima, second minima, and so and so. Central maxima, first minima, second minima, and so and so. Right? So this is the mean diffracted ray. So we are trying to find out the so-called uncertainty, the momentum with respect to this mean deviated ray. Therefore, here we say this is the P. P corresponding to what? The momentum. Right? So here we are finding the position, here we are finding the momentum, that is P. Right? So for that, for diffraction, whether it's electron diffraction or the diffraction of a light beam, the condition for diffraction are always same. So what is the condition? The one. So here you see the condition for first minima. The condition for first minima for the diffraction is what? It is always given by A sin alpha equals to n lambda. So what is A? A is the slit width, the width through which the diffraction is taking place. So in this case, what is A? This is taken as A. What is that A? It is going to be delta x, the slit width, right? So this A is going to be what? It is going to be delta x. A is equals to delta x. Then sin alpha. What is alpha? This alpha is the angle made by the mean deviated ray with respect to the original non-deviated ray. That is this angle alpha, and we are taking the sine of that. So sin alpha, that is equals to n lambda. What is n here? N indicates the order of the spectrum, or the first minima, second minima, third minima, and so on so. So if you take n equals to 1, that corresponds to first order, n equals to 2, second order, so n equals to 3, third order, and so on so. Right? Then what is the lambda? Lambda is the de Broglie wavelength, or the wavelength associated with the electron which is traveling in this direction. So traveling in this, that is, the electron is entering here. It's undergoing diffraction. So this is a diffracted beam. So it is traveling with a particular momentum. So we know that as per de Broglie, whenever a electron or a small particle like electron, proton, neutron is moving with a particular velocity, it is always associated with a wave. That wave we call it what is known as de Broglie wave, and it is having a particular wavelength, what is known as de Broglie wavelength, and that de Broglie wavelength will be given by what? Lambda equals to h divided by p, right? So this is the wavelength associated with the electron which is traveling in this direction. So we have a condition for first minima on the screen. What is the condition? A sin alpha equals to n lambda. Now we know A is delta x. What is alpha? The angle. And what is n? If you take n equals to 1, which corresponds to the first order, so we take, for simplicity, we take it as n equals to 1. So therefore, if you substitute the value here, you can see the moving position. As I explained, uncertainty in the position, that is A is going to be what? Delta x. Then for the first minima, what is the value of n? It is going to be 1. So if you substitute the value of A and n here, what we get? We get delta x into sin alpha equals to lambda, right? Or in other words, from this we can say sin alpha equals to lambda divided by delta x. Sin alpha equals to lambda divided by delta x. Why are we doing all these things? We are doing all these things in order to find out the value of delta px. That is the uncertainty involved in the momentum, right? Now, you can see here the mean value of uncertainty in momentum. The mean value of uncertainty in momentum is given by delta p equals to p sin alpha. Now, how do you got this equation? Delta p equals to p sin alpha. That is, as you can see, the electron is entering here. The electron is diffraction at a particular angle. If there is no diffraction like this, it will be traveled straight like this and falls on the screen, right? So here the electron is traveling a particular momentum. So we are taking a small window and we are taking the two rays. This is the one ray and this is the other ray traveling with a particular momentum called p, right? So now in order to find out the uncertainty in the momentum, so what we have to do? We have to split this momentum into two components. One along the direction, one perpendicular to the direction. So along the direction, the momentum component is going to be p cos alpha. That is, along this same direction, the momentum component is going to be p cos alpha. So this is perpendicular to the incident direction. So in the perpendicular direction, the momentum component is going to be p sin alpha. It's going to be p sin alpha. Since we are taking the mean of all these rays, that is in this direction, which is having an angle of alpha, we are saying that the uncertainty in the momentum is going to be equal to what? Delta p equals to p sin alpha. What is delta p? Delta p is the uncertainty in the momentum. What is p? P is the momentum associated with the moving electron. What is the angle alpha? Alpha is the angle alpha with which the electrons have undergone diffraction or deviation, right? Now, so if we say delta p equals to p sin alpha, what is p? It is replaced by h by lambda. How you got this h by lambda? What is p here? Basically, momentum. What momentum? That is the momentum associated with the electrons or the de Broglie wave, right? So what is that? We know as per de Broglie, lambda equals to h by p, therefore p equals to h divided by lambda. So this is going to be h divided by lambda, it is p h by lambda into what is sin alpha. So here we have sin alpha. What is sin alpha? Sin alpha equals to lambda divided by delta x. Sin alpha equals to lambda divided by delta x. So if you substitute value of p h by lambda into lambda by delta x, what we get? Lambda get cancelled each other. We get h divided by delta x. What is h by delta x? This is the value of delta p. So delta p equals to h divided by delta x. So now we got the value of delta p and we know the value of delta x. This is the value of delta x. That is a is taken as delta x. So in order to evaluate or in order to prove the Heisenberg's uncertainty principle, what we take the equation of Heisenberg's uncertainty principle. That is, therefore delta x and delta px is equals to, so delta x is nothing but delta x value is same. That is, delta x is taken as delta x itself. Then delta px equals delta px. From this equation, it is taken as h divided by delta x. So this delta x, this delta x get cancelled each other. We are left with what? H. And we know that mathematically h is always greater than h divided by 4 pi. So therefore, we can say since h is greater than h divided by 4 pi, we can say delta x into delta px is greater than or equals to h divided by 4 pi. What is this equation? This equation is nothing but exactly Heisenberg's uncertainty equation. That is, delta x, the error involved in the measurement of position, delta px, the error involved in the measurement of momentum is greater than or equals to h divided by 4 pi. So we obtain the Heisenberg's uncertainty equation by using this thought experiment, what is known as diffraction of electrons at a single slit experiment. Using this experiment, what we calculated? We calculated the value of delta x. So this liquid is taken as a delta x. We calculate the value of delta p, right? So by knowing the value of delta x and by knowing the value of delta px, we evaluated the value of delta x and delta px, and we showed that that is equals to greater than or equals to h by 4 pi. Or in other words, we proved or we verified the Heisenberg's uncertainty equation by a thought experiment, what is known as diffraction of electrons at a single slit. So this is one more experiment to illustrate the Heisenberg's uncertainty principle, just like the gamma ray microscope experiment. I think we'll stop at this point. We'll continue in the next class with some other discussion. Till then, take care. Goodbye.